Hi, I am P. Uma Satyakam from School of Electrical Engineering, VIT University, Vellore. I am going to talk about triangular carbon nanotube bundles as VLSI interconnects. My outline is I discuss about interconnects for VLSI circuits, then the background and motivation of my research work, then carbon nanotube interconnects geometry, the transmission line circuit models, then SPICE analysis using smart SPICE, then circuit analysis, and then conclusions and references. Interconnects in VLSI circuits. Interconnects are an integral part of VLSI circuits. They are used to connect the transistors, various logic blocks, and cores in an IC. Interconnects carry clock, power, ground, and many other signals to all the transistors in an IC. Carbon nanotubes, they are the emerging interconnect materials that are used for future next generation interconnects. As the traditional copper interconnects are facing electromigration and grain boundary scattering at 14 nanometer technologies and beyond. So carbon nanotubes they can outperform copper or AL interconnects when used in bundle form. So what is the background of this work? The CNTs are one-dimensional quantum wires. They can be metallic or semiconducting depending on their chirality. Then the metallic CNTs are used for interconnect applications. So the types of CNTs proposed are single wall CNTs, multi-wall CNTs, and mixed CNTs that consist of both single wall and multi-wall CNTs arrayed as interconnects. The transmission line models for CNT interconnects are proposed that include the per unit length equivalent circuit parameters. So the background is CNTs should be used in bundle form as interconnects due to their high quantum resistance of 6.45 kilo ohms per micrometer. Few CNT bundles were proposed as local interconnects by Jihan and Nemi in 2013. MW CNTs are experimentally shown to work at 1 GHz by Philip Wong and team in 2008 and by Kaustav Banerjee and team in 2013. Mixed CNT bundles are also proposed by Majumdar and Kaushik in 2014 and 15 and by us in 2012 and 2013. So motivation of this work is that SPICE simulations show that RC delay and crosstalk induced delay are found to be the major factors that limits the performance. Coupling between adjacent wires is the main reason for crosstalk and high power dissipation. The crosstalk induced delay there are various techniques that are used to reduce the crosstalk between adjacent wires in an IC. So increase the interwire distance, which is a reverse trend against the scaling down approach. It is not a viable option. They use the ultra low K dielectric between adjacent wires. It is a very costly and more fabrication complexities arise and the reliability is a question. So the only way to reduce this problem is to tweak the dimensions or geometry of the CNT bundles for minimum coupling capacitance, which is possible. So in this work we propose that CNT bundle geometry we can be modified from the traditional square or rectangle bundles into triangular CNT bundles. So the number of CNTs in the bundle can be computed as shown, where we can derive the equations using the number of CNTs along the width and the number of CNTs along the height. So the total number of CNTs in the square bundle was found to be around 564 CNTs, where we take HB is equal to WB is equal to 34 nanometers, which is the optimal dimensions at 20 nanometer technology node. On the other hand, for triangular CNTs, the number of CNTs in the bundle can be derived from by knowing the number of CNTs along the base of the bundle. Also, the total number of CNTs that was found was 300 CNTs around CNTs in the bundle, where WB is same as the square bundle. So now we derive the equivalent single conductor RLC parameters to implement the transmission line models of CNT interconnects. So the various RLC parameters include the quantum resistance. The bundle resistance can be given using the distributed RLC parameters, including the quantum resistance, then the quantum capacitance, the kinetic inductance, and the magnetic inductance, and also the electrostatic capacitance between the bundle and the ground. It can be seen that the electrostatic capacitance as well as the quantum capacitance, they are put in series in the circuit diagram, we are having a CMOS inverter as a driver and a load, and we are having a the distributed resistance which is divided by 2 among the 2 contacts in the bundle, and also we are dividing the kinetic inductance among divided by 2 for the bundle. So what is the advantage of using the triangular CNT bundles? Is it advantageous in terms of RC delay, or what is the RC trade-off that we need to see? One of the important things we need to see here is that the width of the bundle for all bundles, it is same as the same for both square as well as the triangular bundles, because the coupling electrostatic coupling capacitance between the bundle and the substrate remains same, which is very easy for comparison. So we had analyzed CNT bundles of dissimilar WB earlier. So results showed improvement in crosstalk delay with increase in number of CNTs in the bundle. So that was previously done by us. So in this current work, what we do is the number of CNTs in the triangular bundle is less than the square bundle. So what is the implications? It implies that the CNT bundles have quantum resistance more than square bundles and quantum capacitance less than square bundles. So the RC delay can be lesser than square bundles. So that is the conclusion that we derive from the bundle structure. So now next we do the SPICE simulations, where we use a driver interconnect load model, where we have the input pulse signal applied to a CMOS driver inverter, which is the driver, and we use a CNT bundle interconnect, and we use a capacitive load model where we take the output. So it can be seen from the graph that we are getting a delay for various bundle types, that is triangular, aspect ratio is equal to 1, 1.5 and 2. It can be seen that the RC delay or the propagation delay, it is least for the triangular bundles, as can be seen for all interconnect lengths of 100 micrometer, 500 micrometer and 1000 micrometers. Also the power dissipation, it is around in the range of microwatts, and it is the least for triangular bundles, as can be seen from the diagram, compared to AR is equal to 1, 1.5 and 2. As a conclusion, it was found that the delay of the TCNT bundles is 46% lesser than square bundles at 1000 micrometers, and also the average power dissipated by the triangular CNT bundles is around 56% lesser than AR is equal to 1 bundles at 1000 micrometers. Capacitively coupled interconnects, we do the SPICE simulations for capacitively coupled interconnects, where we use a driver interconnect load models for both adjacent interconnects in the bundle in the IC. So as can be seen from the diagram, the distance between the corresponding CNTs in the bundle, it increases as we go as we see from the triangular CNT bundles which are coupled to each other. So the equations for coupling capacitance as well as the total coupling capacitance is given below. So the crosstalk analysis of the bundles was performed next, where we use a two interconnects which are placed at a height of ht from the substrate. They are having a height of h and a width of w, and they are separated by a distance of s between each other. And it can be seen that we are using an inverted triangular CNT bundles in the diagram as before we have discussed earlier. This is a question why we are using a triangular CNT bundles from the fabrication point of view. It will be explained in another paper or somewhere else. So these are the results that we have obtained for crosstalk analysis after SPICE simulations. So it can be seen that triangular CNT bundles have around 40, 41 and 33% reduction in delay for 100, 500 and 1000 micrometer lengths when S is equal to W, that is the spacing between the bundles is equal to the width of the bundle. So we also done the simulations where S is equal to W, S is equal to 1.5 W and S is equal to 2 W, that is the change in the spacing of the interconnects. Now obviously it is seen that as we increase the spacing, the delay also reduces, or as we increase the spacing, the power dissipation also reduces. Power dissipation also reduces. So it is seen that For TCNT bundles, around 41, 45 and 44 percentage of reduction in power dissipation was found when compared to square bundles at around 100, 500 and 1000 micrometer lengths for the same conditions of S is equal to W. So this is the ultimate factor that defines the performance of triangular CNT bundle interconnects, that is the power delay product. It can be seen that the power delay product when computed shows that the comparison between the TCNT bundle wires as well as the square bundle wires was plotted with respect to length. So the power delay product increases as the length increases, obviously, and also the power delay product is far lesser than the square bundle wires. So it shows that triangle CNT bundles they have around 48% better lesser PDP than square bundles at 1000 micrometers, so which is an encouraging factor. So as conclusion, we have seen that in this paper triangular CNT bundles has very high speed interconnects is proposed. TCNT bundles show lesser propagation delay and power dissipation than square bundles. Coupling capacitance of the proposed TCNT bundles was modeled and incorporated it in the coupled interconnects model. Transient analysis of 100, 500 and 1000 micrometer wire lengths showed that TCNT bundles performed at least 40% better than square bundles. Power delay product calculations shows that TCNT bundles are the most preferred candidates as VLSI interconnects for future high-speed VLSI circuits. And these are the references for this paper, and we are having around the reference number 2, 3 and 7, which is our earlier work. And this is our research team from the School of Electrical Engineering, VIT University, Vellore. I belong to the Device Research Lab. Mr. Ajay Beast and S. Tandon, they are the BTech Electronics and Instrumentation Engineering students. And Dr. Parsati Malik is the Professor and Director of Ranking Accreditation Cell from VIT University, is my mentor and guide. Thank you.